Good morning, everyone. So what I'm showing you on this slide to start off this pre-lecture tutorial is the excerpt of the data packet that you would actually get to take the AP Chemistry exam, and specifically the excerpt that relates to gases. Now there's also stuff in here about liquids and solutions, which we will be getting more involved with towards the end of the year, but in general the amount of information, as you can see, is somewhat small. And if all you have is an ideal gas law problem, then basically all you need is an expression of the ideal gas law, and that's pretty much it. You know, you would be able to plug in variables and solve. But you might also be asked to, say, manipulate Boyle's law, or to manipulate Charles's law, or one of the other individual laws that contribute to the ideal gas law. And sometimes, especially when you're stressed and when you're trying to work quickly, it might be possible that you may not remember the formula, or you might remember it incorrectly. And so the first thing I want to show you in this tutorial is how to derive the individual gas laws from the ideal gas law. So what we have here is the ideal gas law, and all the variables have been labeled. Now let's actually see if we can piece together the individual gas laws that contribute to it by holding pairs of variables constant. So for example, if I want to write an expression for Boyle's law, well, that's the law where I'm trying to examine the pressure-volume relationship at constant temperature and with the number of moles of gas also constant. So if I rewrite the ideal gas law, notice that all of the things that are constant, number of moles, ideal gas constant, and the temperature, all of these things are on one side of the equation, and all the variables are listed on the left-hand side of the equation. So that means I could group all of these three quantities together and simply write that if I'm at a scenario where I have constant temperature and constant number of moles, the product of the pressure and the volume must equal some constant, and that is the expression of Boyle's law. And if I'm dealing with an initial set of conditions, P1, V1, and a final set of conditions, P2, V2, then I could also write this law as P1, V1 is equal to P2, V2. All right, now let's see if we can piece together Charles's law. So that's Boyle's law, Charles's law. Okay. At that particular point, we would be looking at the volume-temperature relationship, so that means at constant pressure with constant number of moles of gas. So if I rewrite the ideal gas law, that's PV equals nRT, I'm going to go and rearrange the ideal gas law so that all of the constants, the pressure, the number of moles, the ideal gas constant, all of these will appear on the same side of the equation, and all of the variables, the things that will change, the volume and the temperature, they're going to be on the opposite side of the equation. So if I do that, what I get is the volume over the temperature is equal to nR over P. And again, since all of these quantities actually are being held constant for this scenario, then that would mean that the volume over the temperature is equal to some constant. If I'm considering, again, initial and final conditions, then this could also be written as V1 over T1 is equal to V2 over T2. Now, let's actually see if we can piece together Avogadro's law. Okay, well, that would be the volume relationship as compared to the number of moles. So that means I'm going to hold temperature constant. I'm going to hold the pressure constant. So pressure and temperature both constant. Again, if I rewrite PV equals nRT, in this particular case, my constants would be P and T. Now, what I'm going to do is I'm going to go and also the ideal gas constant, sorry. The other thing I'm going to do is put all the things that are changing, the volume and the number of moles, on one side of the equation. So if I do that, that's V over N is equal to RT over P. Grouping all of these quantities together as a constant, that's the volume over the number of moles is constant. If I have initial and final conditions, then this would be written as V1 over N1 is equal to V2 over N2. One law that is actually discussed in the first year of chemistry that we don't really seem to delve into all that much, or at least your book doesn't, is what we called last year the Gay-Lussac law. Or your book actually, if you take a look through some of the online items, they also call this Amundsen's law. And all that is, it's the pressure-temperature relationship holding volume and number of moles constant. So, again, I would start with the ideal gas law. All right, I'm going to be holding volume, number of moles constant, as well as the ideal gas is always a constant. So if I am looking to vary pressure and temperature, then if I rearrange this, putting all of the things that vary on one side and all of the constants on the other, I get P over T is equal to NR over V. Again, all of these things are held constant, so that means P over T is equal to some constant, provided that these conditions hold, and I get P1 over T1 is equal to P2 over T2. Okay, so if we also hold only one variable constant, all right, suppose we only hold the number of moles constant and let everything else vary. Well, PV is equal to nRT. So since I'm holding only the number of moles constant, and the ideal gas constant obviously is always a constant, with everything else changing, then if I pull all the variables to one side of the equation, I get this. If this is a constant, that's PV over T is equal to some constant, or if I have two conditions, initial and final conditions, that's P1 over V1, P1 V1 over T1 is equal to P2 V2 over T2, and you should be able to recognize this as the combined gas law. All right, now it's not just important to be able to realize what happens with the variables that are shown in the ideal gas law on its own. It is possible to actually relate density and molar mass of the gas in question to the rest of the quantities in the ideal gas law. And so your book takes you through this, but I'll sort of give you the rundown once again. And the key here is to use this relationship and that one. This reminds us that the number of moles is equal to the mass over the molar mass. And again, this reminds us that density is equal to mass over volume. So let's go and let's actually substitute in for mass terms for the number of moles. So for example, this would be PV is equal to the mass of the gas over, the mass of the gas times the ideal gas constant times the temperature over the molar mass. So again, the small m is our mass, the large M is our molar mass. And so if I rearrange this a little bit, all right, if I go and move volume to the other side of the equation, mass over volume is just density. So that means that the pressure of a gas is equal to its density times the ideal gas constant times the temperature over its molar mass. Now I can do two things with this. I can solve in terms of density, in which case the density will be the pressure of the gas times its molar mass divided by the ideal gas constant times the temperature, or, and that's again if I'm trying to calculate density explicitly, or if I want to calculate the molar mass of a gas, provided I have the rest of the data that's present in the equation, then the molar mass is equal to the density times the ideal gas constant times the temperature over the pressure. So each of these relationships, again, might be necessary on problems in working the AP Chemistry exam, but if you don't happen to remember them, just bear in mind that with a little bit of thought, you are able to sort of derive them if you need them. So let's take a few examples of using some of these relationships. Here, I'm asked how many moles of gas occupy 98 liters at a pressure of 2.8 atmospheres and a temperature of 292 Kelvin. So basically, this is a straight up application of the ideal gas law. And so if I want to solve for the number of moles, then that would be PV over RT. I would substitute in 2.8 atmospheres times the volume of 98 liters over the ideal gas constant, 0.0821 liter atmospheres per mole Kelvin, times the temperature, which is 292 Kelvin. So my kelvins would cancel, so would my liters and atmospheres, leaving me only in units of moles, as it should be. And so if I do that math, I should get 11.4 moles. Okay. Now, what about this problem? It says a balloon is filled with 35 liters, that's a volume, of helium in the morning when the temperature is 20 degrees Celsius. So that's a temperature. Okay. By noon, the temperature has risen to 45 degrees Celsius, so that's a second temperature. What is the new volume? I'm being asked for a V2. What's the new volume of the balloon? And V1 must be the 35 liters. So this is a Charles law relationship. So again, based on what we discussed earlier, that's V1 over T1 is equal to V2 over T2. Solving for V2, V2 is equal to V1 times T2 over T1. Okay, substituting in. My V1 was 35 liters. My T2 was 45 degrees Celsius, but remember, all gas law problems involving Charles's law, involving the ideal gas constant, all of these problems must have temperatures in units of Kelvin. So you must add 273 to the 45 degrees Celsius and the 20 degrees Celsius. That makes 45 degrees 318 Kelvin. You're going to divide that out by 293 Kelvin, which is 20 plus 273. And when you do this math, you get 38 liters. Okay, last problem. It says determine the density of oxygen at STP. Now, these problems are always a little tricky because it looks like they're practically giving you nothing. But keep in mind that at STP, that means my temperature is 273 Kelvin. And the pressure is 1 atmosphere. They're giving you the identity of the gas. That means automatically I know its molar mass. The molar mass of diatomic oxygen is 32 grams per mole. And so if you recall, basically if I want the density, that's the pressure, times the molar mass divided by the ideal gas constant times the temperature, based on our derivation on the previous slide. And so if I go ahead and substitute in, the pressure is 1 atmosphere, the molar mass is 32 grams per mole, the ideal gas constant we know, 0.0821 liter atmospheres per mole Kelvin, and the temperature was 273 Kelvin. If you cancel everything out, you'll see that you're left in units of grams per liter, which are actually density units. And if you do this math, you get 1.43 grams per liter. So try the follow-up assignment where you apply these gas laws. We'll discuss this topic more tomorrow. If you have any questions, again, email or ask me in class. Have a good night.